So for today's lesson, we're going to solve some sample problems from magnetostatics. So let's start. So for our first problem, a beam of protons, which has a charge of 1.6 times 10 raised to negative 19 coulombs, moves at 3.0 times 10 raised to 5 meters per second through a uniform 2.0 Tesla magnetic field directed along the positive z-axis. Okay? The velocity for each proton lies in the xz plane, as you can see in the figure, and is directed at 30 degrees to the positive z-axis. Find the force on a proton. Okay. So for us to find that force, we need to use our the magnetic part of the Lorentz force law, which is the QV cross B. If we just want to know the magnitude, okay, we can use your QVB sine phi, okay, which is if we want to know the entire vector, okay, we're going to calculate the magnetic force, okay, we're going to use the vector form of the velocity and the magnetic field, okay. So for the magnitude, we know that we can just use QVB sine phi. Sine phi is the angle between the magnetic field and then the velocity. So substituting the values, that would be 1.6 times 10 raised to negative 19 coulomb times 3.0 times 10 raised to 5 meters per second times 2.0 Tesla times sine 30 degrees. It will give us a magnitude of the magnetic force that is 4.8 times 10 raised to negative 14 Newton. As you can see, the magnitude is really small. Okay, but take note that this force is enough to deflect, okay, the trajectory of the charge. Okay. So for us to know the direction, okay, we need to use the entire form of the magnetic force with respect magnetic force due to the magnetic field, which is QV cross B. Okay. So for our velocity vector is now in this form, 3.0 times 10 raised to 5 meters per second sine 30 degrees I hat plus 3.0 times 10 raised to 5 meters per second times cosine 30 degrees. Okay. Take note that based on the problem, the velocity, okay, of each proton lies in the xz plane, as you can see here. So that's why you have I hat and k hat here. Okay. And then it is directed at 30 degrees, okay, to the positive z axis. Okay? That's why you have this angle here. Okay. So this is a take note that this is still a right hand coordinate system. Okay. So x, positive y, and positive z. Okay. So take note that we use the sine 30 for getting the x component because your angle is referenced along the positive z-axis rather than the positive x-axis. So for us to get the x component, we're going to use the sine 30 degrees. Okay. And for us to know the z component of velocity, we're going to use the cosine 30 degrees. Okay. So now we have also the magnetic field, which is directed parallel to the z-axis. So the vector notation form that would be 2.0 Tesla k hat. Okay. So performing the cross product. Okay. So if we do this, okay. So what happens? So 1.6 times 10 raised to negative 19 coulomb. Okay. 3.0 times 10 raised to 5 meter per second. Okay. And then times 2.0 Tesla times, okay, our vector cross k hat. Okay. So I hat, this is the x component. We're going to cross it with k, and then we'll also cross the 30 degrees. Okay, k hat with k. So k cross k will give you what? Will give you 0, right? And then I cross k, remember our mnemonics. Okay, so I, j, and k, counterclockwise positive. So I cross k, that is I, j, k. So I cross k, that would be a clockwise rotation, that would give you negative j. Okay, so the answer is, okay, after you substitute this into your calculator, the answer would be negative 4.8 times 10 raised to negative 14 Newton J hat. Okay, so in this case, our particle, our proton, is moving along this direction, and it is being deflected by a magnetic force that is along the y-axis. Okay, and since our value of the magnetic force is negative, it means that the magnetic force is pointing downward into relative to this plane. Pointing downward relative to this plane. Okay, so take note, class, that if your proton is an electron now, you replace the proton with an electron, same specification in the problem, you will just see that you will just going to reverse the direction of the force. Now it is directed along the positive y-axis, okay? But still, same magnitude since you have the same fundamental charge for both the protons and the electrons, okay? So that's our first problem. So for our second problem, just an analysis, okay? Okay, so in this diagram, you can see that you have an electron that is going along the path, okay, 1, 2, and 3, okay? So a particle with a negative charge moves in this plane, okay? Which path, 1, 2, or 3, does the particle follow? Of course, you have an answer here, which is path 3. But the question is, how, okay? So remember that this charge will experience a magnetic force due to the magnetic field, okay, that is perpendicular to the motion of the particle. So if your V is going to the positive x-axis and then the magnetic field is into the plane, if you use your right hand rule, you can see that if this is a positive charge, the direction of the force is upward. Okay? If this is a positive charge. Okay? So for a positive charge particle, it will follow a path 1, okay, trajectory. But since we have an electron here, you need to flip the direction of the force. That's why this electron will follow the third path. Okay? So the trajectory of this electron is described by this path 3 because the force will be directed downward. Okay? Always remember that your magnetic force is perpendicular to both the velocity and the magnetic field. Okay, second question, or third question, I mean. How about the path 2? What will make the electron to just pass through it, okay, following the trajectory in this described by path 2? Okay, what would be the orientation of the field and the velocity vector? Okay, so remember, our magnetic force is QV cross B. V cross B will just become 0, okay? Or in general, the magnetic force will become 0 if V, the magnitude of V, or the magnetic field B is 0, or the direction, I mean the orientation of the direction of both the vector quantities. So if V, or the velocity vector, is parallel to the magnetic field vector, okay, there will be no force. Okay, so path 2 is only possible if the velocity vector V is parallel to B. Okay, or if the magnitude of the magnetic field B is 0. Of course, you cannot take the velocity vector of the electron to be 0 because it will not follow this path. So there are two ways for you to follow the path number 2. Number 1 is that the velocity vector is parallel to the magnetic field, or the magnetic field B magnitude is equal to 0. Okay, so the electron will just go through an empty space. Technically, there's no influence of the magnetic field. Okay, so that's a good insight problem. For our third problem, figure 27.16a is a perspective view of a flat surface with area 3.0 square centimeters in a uniform magnetic field B. Given with the magnetic flux through this surface to be positive 0.90 milliweber, find the magnitude of the magnetic field and the direction of the area vector A. Okay. So we're going to solve for the magnitude of the magnetic field, and then we're going to look for the angle. Okay, technically, what is the area vector A? So if you can remember, our expression for the magnetic flux is the integral of B dot dA. Okay, so the dot product of B and dA, and then you take the integral of it. Okay. Now that we were given with magnetic flux, and somehow the geometry of our problem is easy, technically the problem gave us already the surface area. So there is no need for to do the complicated integration into the problem. You can just integral dA, which will give you A, which is the area of this surface. Okay. So for our equation, that would be okay this. So remember, B dot dA, or now it's B dot A, will give you B A cosine phi. So what is the phi? The phi is the angle between the surface normal and the magnetic field. Now we were given with this plane, which is inclined 30 degrees. Okay. We want to know the surface normal, the unit vector that is perpendicular to the surface. And for us to do that, we look at this sketch. Okay. So as you can see in this orientation, this is 30 degrees. Okay. And we can see that the angle between the magnetic field B and then the surface normal is 60 degrees. Okay. Somehow, okay, the inclination of the surface normal is 60 degrees above the positive x-axis. Okay. So that's what we're going to supply here. Okay. So we're going to supply here. So if we substitute the values, do not forget to convert, okay, your values. So for example, 0.90 milliweber is equal to 0.90 times 10 raised to negative 3 Weber divided by 3.0 times 10 raised to negative 4 square meter, okay, which is 3.0 square centimeter times cosine 60 degrees, and it will give us 6.0 Tesla. Okay. So that's the answer. So the magnetic field is equivalent to 6.0 Tesla. Okay. That's the amount of magnetic field passing through this area. Okay. How about the direction? The direction is 60 degrees. Okay. So that's our third problem. Next problem. A magnetron in a microwave oven emits electromagnetic waves with frequency f equals 2450 megahertz. What magnetic field strength is required for electrons to move in circular paths with this frequency? Okay. So we can execute our problem through this. Okay, so the angular speed that corresponds to the frequency f is omega equals 2 pi f. So you multiply your given frequency, which is 2450, okay, megahertz, convert it into per second or in hertz, that is 2450 times 10 raised to 6 hertz, okay, and then multiply it to 2 pi, okay, and then the angular frequency would give us 1.54 times 10 raised to 10 hertz. Okay, so from our equation, okay, B equals mq over absolute value of q, substituting all the values, that is 9.11 times 10 raised to negative 31 mass of the electron times the angular speed, the angular frequency of the electrons, okay, moving in such circular paths, okay, divided by the fundamental charge. Okay, so magnetic field, okay, so the magnetic field strength required for you to move the electrons in a circular path is corresponding to 0.0877 Tesla. Okay. So take note, class, that this amount of magnetic field is somehow moderate, okay, and this can be easily produced, okay, with a permanent magnet. Okay. You can also use an electromagnet to produce that amount of magnetic fields. That's why you can create circling electrons in a magnetic field. Okay. So incidentally, the 2450 megahertz electromagnetic waves are useful for heating and cooking food because they are strongly absorbed by water molecules. Take note, just a trivia. Okay, 2450 megahertz is equivalent to 2.45 gigahertz. Okay, take note that 2.5 gigahertz, okay, is somehow in the range of our Wi-Fi. Okay, so the same technology is being used in microwave, except that in microwave you are using it to heat the food, okay, not to transmit information. Okay, that's our um, that's our problem. Next problem. In a situation like this shown in this figure, the charged particle is a proton, okay, and the uniform zero point 0.5 Tesla magnetic field is directed along the x-axis. At t equals 0, the proton has velocity components Vx equals 1.50 times 10 raised to 5 meters per second, By equals 0, and Bz to be 2 times 10 raised to 5 meters per second. Only the magnetic force acts on the proton. Letter A. At t equals 0, find the force on the proton and its acceleration. Letter B. Find the radius of the resulting helical path, the angular speed of the proton, and the pitch of the helix, okay, or the distance traveled along the helix axis per revolution. Okay. So letter A, okay, at time equals 0, we need to know the amount of force on the proton and its acceleration. So of course, there is an external force acting on the proton. Of course, that proton will accelerate. Okay. And then letter B, we actually anticipate that this proton will move in a circular motion. But since you have a Vx, okay, which is the velocity along the x-axis, it means that it is also moving parallel to the magnetic field. Okay, we are expecting that this proton will move in a spring-like, okay, spring shape, or helical, in a helical way. And the letter at least the last, let's say call it letter C, find the pitch. Okay, so the pitch would be the distance between these two. That's the pitch. Okay, so what would be the pitch of this helix? So for letter A, we express our magnetic field and velocity vector as vectors, okay, with vector components, okay, written in vector notation form. Since our velocity has only two components, one along the I and one along the k hat, okay, or one along the x, one along the z axis, if we use our expression, which is qv cross b, okay, we can get that the magnetic force would be directed along the y-axis. Okay, so since we have these values, the values for the velocity, the magnetic field, and the charge, we can see that the magnitude and the direction of the force would be 1.60 times 10 raised to negative 14 Newton. Okay? Directed positive, positive y-axis. And then from our Newton's second law, that would be equal to, the acceleration would be equal to F over m. Okay, so our vector is 1.60 times 10 raised to negative 14. And then the mass of the proton is 1.67 times 10 raised to negative 27 kilograms. Okay, it will give us an acceleration that is really, really huge, 9.5 times 10 raised to 12 meter per second squared. And also along the same direction as the force. It's the Newton's second law, the premise of the Newton's second law. Okay, so the direction of the force is the direction of the acceleration and vice versa. the object will accelerate, okay, along the direction of the force. Okay. So that's our first answer, the force and the acceleration. Next. Okay. What's next? So next, we need to know the radius. Okay, so we do have an equation for this that we discussed in our lecture that is equal to, okay, the technically mv. Okay, somehow it's the momentum. Okay, so m times the velocity. Okay, that is perpendicular to the magnetic field. Okay, it's not actually momentum, but it looks like. Okay. So mv sub z over q times b, absolute value of q, whether you have an electron or a proton. Okay. So the radius would be the ratio of the product of the mass and velocity and the product of the charge and the magnetic field. Okay, you just substitute the values and you will have 4.18 millimeters. Okay, so that's the radius of this helical path. Okay. And then next, we need to know what would be the pitch. What would be the distance between two successive revolutions? So from our angular speed, okay, we're going to get the period. Okay, so one, we get the angular speed or the angular frequency. And since the angular frequency has a relationship with the period, okay, we're also extracting the period. And then after extracting the period, we're going to use that time to calculate the distance. So remember, our equation for distance is S equals to VT. Okay? Actually, this is displacement. Okay? If you just want the speed, okay, it's just S equals VT. Okay? So that's the speed of the proton. So now we get the angular speed first, or the angular frequency, that is equivalent to qv over m. Okay, substitute the values, and then you will have this 4.9 times 10 raised to 7, okay, rad per second. It's the unit of angular frequency. Okay. Take note that the relationship between the angular frequency and the period is equivalent to 2 pi over omega. Saan nanggaling yun? Okay. So remember that f is equal to 2 pi, okay, omega. And f is equivalent to 1 over the period. Okay. So if we have this and the period is 1 over t, therefore the period is equal to 2 pi over omega. Okay. So upon substituting the value of your angular frequency, which is 4.9 times 10 raised to 7 rads per second, okay, or radians per second, the answer would be equal to 1.31 times 10 raised to negative 7 seconds. So that's the amount of time, okay, to get a full revolution. But since this is a helical path, one full revolution will give us a distance, okay, which is equal to Vt. Okay, it means that from from one point, you're going to move from this point to this point after that amount of time, that amount of period. Okay, and that entire revolution will make the proton to be in this point, okay, to this point. Okay, so that's the entire time of revolution, that is 1.31 times 10 raised to negative 7. But since this is also moving parallel to the magnetic field, parallel to the x-axis, okay, it will move this distance. So if we know this distance, we will know the pitch of this helix. Okay. So using our basic kinematic equation, which is speed equals, distance equal to speed times time. Okay, from speed is equal to distance over time. So we substitute the time to be 1.31 times 10 raised to negative 7 seconds, and then the velocity along the x-axis is 1.50 times 10 raised to 5 meters per second. That pitch, okay, is equivalent to 19.7 millimeter. So that's it. Okay? So this is the dynamics and the kinematics of this proton moving, okay, parallel and perpendicular to the magnetic field. Okay? So this happens, this helix path, okay, this helical motion occurs when the proton has a component that is parallel to the magnetic field, or an electron is moving with a velocity component parallel to the magnetic field, and at the same time perpendicular to the magnetic field. Okay, that's our problem. There is almost no helium in ordinary air. So helium sprayed near a leak in a vacuum system will quickly show up in the output of a vacuum pump connected to such a system. You are designing a leak detector that uses a mass spectrometer to detect He positive ions. Charge is positive E 1.60 times 10 raised to negative 19, and the mass of the helium ion would be 6.65 times 10 raised to negative 27 kilograms. Ions emerge from the velocity selector with a speed of 1.00 times 10 raised to 5 meters per second. Meter per second. Meters per second. They are curved in a semicircular path by a magnetic field B prime, okay, and are detected at a distance of 10.6 centimeters from the slit S3, as you can see in this figure. Okay, calculate the magnitude of the magnetic field B prime. Okay, so we have two magnetic fields here. The first one is the magnetic field inside the chamber, and the second one is the outside magnetic field that would make this particle, the helium ions, to curve. Right? So this is the setup of a mass spectrometer. Of course, uh, the greater the mass of the particle, the greater the radius, right? Because it will be harder. It will be harder to deflect them, okay, if they have greater momentum in motion. Okay. So from our equation, okay, which is R, in getting the radius of the curvature of this charged particles once it is now outside the velocity selector, okay, that is mv over qb, we can solve for the b prime. We are not interested in the magnetic field inside the mass spectrometer because that magnetic field, okay, together with the electric field will apply a balancing force on the proton. That's why you have this velocity selector here. Okay, the only thing, okay, that will deflect the motion of the charge when it is now outside the velocity selector is the B prime magnetic field, which is the magnetic field that we want to solve. So B prime is equal to mv over qr, derived from our original equation for solving the radius of curvature, and then substituting the values into the equation, it will give us 0.0818 Tesla. So that's the required magnetic field, okay, in a device that you want to use, or leak detector that you want to use for us to detect the He ions. Okay, so that's it. A straight horizontal copper rod carries a current of 50 amperes from west to east in a region between the poles of a large electromagnet. In this region, there is a horizontal magnetic field toward the northeast that is 45 degrees north of east with magnitude 1.20 teslas. Find the magnitude and direction of the force on a 1 meter section of rod. Letter B, while keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? What is the force magnitude in this case? So if you can remember, okay, so we have the QB cross B for moving charges. Now we have just a current segment. Okay. So in this segment, somehow a 1 meter section of the rod, it is being exposed to a magnetic field. So what is the force on that segment? Okay. We can use our equation for the force for a current segment, which is IL cross B. But since we're just looking first for the magnitude of the force in this orientation, so here's the orientation or this is the setup of the problem. You have this segment of the wire where it carries 50 amperes of current, and then the magnetic field, which is 1.20 Teslas, or magnetic flux density equivalent to 1.20 Teslas, is around 45 degrees relative to the wire. Okay. So based on this, what will be the magnitude and what will be the direction of the force? So from IL cross B, we have the ILB sine phi, where the sine phi is the sign of the angle between the magnetic field and the direction of the current segment technically. So here we have the current segment to be 1 meter, and then the current is 50 amperes, and then the magnetic field is 1.20 Tesla, and then the angle between the magnetic field and then the current segment is 45 degrees. Therefore, if you multiply all of these quantities, the answer will be 42.4 newtons. Okay, so that is the amount of force that this current segment is experiencing at this orientation. For the next problem, while keeping the rod horizontal, what should it be? How should it be oriented to maximize the magnitude of the force? Remember that to maximize the force, we need to make sure that the direction of the current or the current segment will be perpendicular to the direction of the magnetic field. Okay, so that's the maximum. So for us to do that, we need to rotate this current segment by 45 degrees clockwise so that the current segment will be perpendicular to the magnetic field. And we can see that we can increase the force, as you can see here in this red circle. It means that this is the tip, okay, of the force. It means that the force is out of the page, out of this screen as you watch it. So you can increase the magnitude of the force, okay, if the current segment is perpendicular to the magnetic field. So the force is now equal to ILB only because sine 90 gives you 1. And the maximum force is 60 newtons. So that's the maximum force that is possible in this configuration. Okay, 50 amperes in the wire, perpendicular segment of this rod to the magnetic field. In that figure, the magnetic field B is uniform and perpendicular to the plane of the figure, okay, pointing out of the page. As you can see, this is the magnetic field, the blue ones. Okay. The conductor, okay, carrying current I to the left has 3 segments. One, a straight segment with length L perpendicular to the plane of the figure, which is this. That's why you can see it here. Okay. The number 2, a semicircle with radius R. And 3, another straight segment with length L parallel to the x-axis, which is this one. So you have this one. Okay, this is the first part. Technically, you can extend that wire out of this page, but the current is into the page. That's why you have this in. Then the current flows to the semicircle, okay, segment, and then to the straight segment that is parallel to this plane. Okay, find the total magnetic force on this conductor. So by just looking at this problem, we can separate the calculation of the magnetic force for 3 segments. Number 1 is for the perpendicular segment. For this, then we're going to solve for the magnetic force due to the magnetic force applied on the semicircle conductor, and then the force that this straight wire will feel due to its orientation, okay, which is parallel to the plane, parallel to the x-axis specifically. Okay. So how are we going to solve this problem? So first is that we represent our magnetic field in vector form. And now this is xy plane, therefore the direction that is outward of the page would be the positive z axis. And since you can see the dots are uniformly placed in space, therefore we can say that the magnetic field is uniform. Okay. Then we're going to find F1 and F3, okay, on the segments 1 and 3. Okay, so F1 would be this one, okay, for the first segment, the perpendicular one, and then F3 for the parallel to the x-axis segment, okay? And then later on, we're going to solve for the magnetic force on the semicircle, which is a little bit complicated because of the semicircle geometry, okay? For the curved segment, okay, we will divide this entire semicircle into infinitesimal straight segments where df2 will act. And then we're going to integrate for the entire semicircle. For segment number 1, we can see that L is equal to negative LK hat. It means that the entire length of this wire is parallel or anti-parallel to the magnetic field. That's why if we take the cross product of this wire segment to the magnetic field, the answer would be equal to 0. For the segment number 3, we can see that this is directed towards the negative x-axis. That's why you have negative Li hat. If you get the cross product of I and k, and then you take the negative of it, it will be positive j, because I cross k gives you negative j hat. Negative j hat times negative 1 will give you positive j hat. Okay. And then I, L, and B are all constants. So now we already know the forces on the first segment and the third segment. We're going to solve for the second segment, which is the curved segment. In this case, somehow the dl is related to the d theta, okay? And then this dl can be represented by r d theta. And somehow it will be easier to integrate with respect to theta rather than dl. So we're going to integrate with respect to d theta. That's why we represent dl as r d theta. Okay. Take note that dl cross b is radially outward from the center. How that's possible? How is it possible? So look at dl here. Okay. Take note that dl cross b will give you this df. You can use your right hand rule to verify that. So the index figure would be the dl, and then the middle finger is the magnetic field that is pointing towards you, and then the thumb is the df here. Okay. So just imagine that if your dl is upward here, you can say that your df is pointing to the positive x-axis. If you are at this point, okay, 90 degrees from the x-axis, your dl is directed towards negative x-axis, but the force is toward the positive y-axis. And then you will do it for every segment that you will define, okay? And then integrate it. Always remember that D, L, and B here, in this case, are perpendicular because you have a semicircle. It means that DL is tangent at every point in this semicircle. If you have an ellipse, then DL and DL and B is still perpendicular, but somehow DL is not. It's still be tangent, but it would have a harder solution. Yeah, it would be more complicated because it is not a semicircle but an semi-ellipse, like that. Okay. So next is that we define df based on our equation for the current carrying wire, which is IDLB. We replace dl, okay, with r d theta because we're going to integrate with respect to d theta rather than with respect to dl. Now we have this expression, okay? So df2 has two components, dfx and dfy. If we get the dfx first, we need to use the cosine theta, okay? Because the angle here is defined along the x-axis, and this angle is equivalent to this angle here. Then, if we define df2y, okay, that's the y component of df, that would be equal to ir d theta b sine theta. And then we know that the limits of integration will be from 0 to pi, or 180 degrees. So if we integrate this df2x and df2y to get the total x component and the total y component, this would be the answer. Okay, so the integral of cosine theta is sine theta. If you take it from 0 to pi, sine 0 is 0, and then sine pi is 0. Therefore, f2x is equal to 0. Just imagine that all of this fx, okay, from this point, okay, from this point up to this point, okay, would be all directed, okay, to the x-axis. Actually, there would be no x component at this point because all of the forces would be along the y component. But take note that if you move, okay, move again from, I think this is pi over 2 to pi, okay, you can see that all of the dfx, okay, will be now pointing to the left. It means that the left side will cancel the right side when it comes to the x component of the force. And the only force that will be left would be all directed parallel to the y axis. That's why you have this equation, because if you integrate that sine theta d theta from 0 to pi, it will give you negative cosine, okay? And then substitute negative cosine pi minus, it's now plus, so negative cosine pi plus cosine 0, that will give you negative times negative 1 plus 1, which is 2. Okay? So that's why you have 2IRBJ. Okay? And now, we're talking about the total magnetic force for the entire segment. We just add all of the forces that we got. So F1 is 0, then F2 is 2IRBJ hat, and then F3 is ILBJ hat, which is also along the y-axis. That's why you have the J hat. And the answer, the total force would be IB times 2R plus L, quantity J. Okay. So remember that in this kind of problem, you can separate the segments, okay, to solve for the forces, and it will make your calculation easier. And then you just add all of them because this is just a force. You're just looking for the amount of force applied to the entire segment. Of course, the level of calculation will be more complicated if you have a squiggly line segment here. Okay? It will be easy if this is just a part of a square or semi-square, half of the square, or just a it looks like this one, like that one. I don't know what how do you call that shape. Okay. Just straight segment, but in a with a turn 90 degrees. Okay. So this is the solution for this problem, and I hope you learned something from this. Thank you. A circular coil 0.05 meters in radius with 30 turns of wire lies in a horizontal plane. It carries a counterclockwise, as viewed from above, current of 5 amperes. Okay? So the current within the coil is 5 amperes. The coil is in a uniform 1.2 Tesla of magnetic field directed toward the right. So this is the orientation. Find the magnitudes of the magnetic moment and the torque on the coil. For the magnetic moment, we know that the equation is NIA. So the number of turns times the current times the area that is enclosed by the coil. Okay. Take note that if you ask for the direction of the magnetic moment, that would be perpendicular to the bound surface. Okay. But for the magnitudes, okay, it's just NIA. So 30 times 5 amperes times pi times the square of 0.05 meters, because that's the area of the circle. So the magnetic moment would be 1.18 ampere square meter. Okay. And then for the torque, we can use the magnetic moment, okay, because we have mu cross B. And since we're just getting the magnitude, we just need to solve mu B sine phi. Okay, the sine phi or the phi is the angle between the magnetic field and the magnetic moment. Okay. So that is 90 degrees. Okay. So based on the diagram. So the answer would be 1.41 Newton meter. Okay. So always remember this, class. The magnetic moment, okay, and the torque, if they are, if you have a magnetic moment and then you expose a you let it to be exposed in a magnetic field, that magnetic field will try to apply a torque, okay, on that coil so that the magnetic moment will be parallel to the magnetic field. Take note that the magnetic moment, if it is opposite in the direction of the magnetic field, it is unstable equilibrium. It means that um, a small perturbation, or what do you call this? A small nudge, okay, to the coil will bring back that coil parallel to the magnetic field. If the magnetic moment is already parallel to the magnetic field, it will not experience any torque at all. Okay? The torque will diminish because the magnetic moment is now parallel to the magnetic field. Okay? So take note that this torque vanishes when they are already parallel. The magnetic moment and the field are parallel. Okay? The maximum amount of magnetic torque can be experienced when the magnetic moment is perpendicular to the magnetic field. That's it for this problem. A Hall effect measurement. You place a strip of copper 2.0 millimeters thick and 1.50 centimeters wide in a uniform 0.40 Tesla of magnetic field as shown in this figure. Okay, as you can see in the screen. When you run a 75 ampere of current in the positive X direction, okay, you find that the potential at the bottom of the slab is 0.81 microvolt higher than at the top. Okay. From this measurement, determine the concentration of mobile electrons in the copper. So if you can remember in our Hall effect topic in the lecture, we have an equation that we can use to solve for the mobile number of mobile concentrations, which is equal to NQ. Okay, here NQ equals negative JXBY over EZ. Okay, if you just want to know the concentration, which is the N, okay, just divide both sides by Q. But before we solve for that, we need to know Jx and Ez. So Jx is just what? The current density. Okay, so it is the current uh, per area perpendicular to the flow of the current, because this A is the cross section. So what is the thickness of this conductor? The thickness is 2.0 millimeters, and the width is 1.50 cm. So if you want to get the area, the cross-sectional area, you just need to multiply that 2. Okay? So 2.0 times 1.50. Of course, you need to convert. So it's 0.002 meters times 0.015 meters, okay, to get the cross-sectional area, as you can see here. Okay? And then the current is 75 towards the positive X direction. And then we can also solve for the Hall EMF, or the Hall voltage, because we were given with the potential that is 0.81 microvolt higher than the top, at the top than the bottom. Okay, so the voltage between between the sides, between the bottom and top part, okay, would be 0.81, okay, times 10 raised to negative 6 volts. And then you divide it with the uh this is the, I think this is the width. Okay, so the width of the conductor, which is 1.5 times 10 raised to negative 2 meters. Now that we now have the values for Jx and Ez, we can now solve for the concentration of the mobile electrons in the copper. So we have an equation which is NQ equals negative Jxby over Ez. Okay. Then we just divide both sides by Q, which is the fundamental charge, and substitute all of the values given, and then the solved values for Jx and Ez will have this answer. Okay, so the concentration of mobile electrons in copper is 11.6 times 10 raised to 28 per cubic meter. That's the amount of electrons that you have per a cubic meter of the conductor of this copper. So if you were given, if you were given with a 1 cubic meter of copper, you expect that the concentration of mobile electrons in that copper, okay, in that cube of copper, okay, would be this amount, 11.6 times 10 raised to 28, okay, per cubic meter. So the actual value of N for copper is 8.5 times 10 raised to 28 per cubic meter. Okay, so the difference shows that our simple model of the Hall effect, which ignores the quantum effects and electron interaction with the ions, must be used with caution. That's why I said that there's quantum Hall effect. Okay, there's in the quantum realm, there's some kind of electron interactions. Okay, that needs new physics, okay, rather than the classical one that we're talking about right now, which is the classical Hall effect. Okay. So take note that even that with good conductors, the Hall EMF is very small, even with large current densities. Okay. In practice, Hall effect devices for magnetic field measurements use semiconductors, okay, as materials, for which moderate current densities give much larger Hall EMFs. Okay. So that's it for this problem. Forces between two moving protons. Two protons move parallel to the x-axis in opposite directions at the same speed v, okay, which is small compared to the speed of light c. Okay, at the instant shown, find the electric and magnetic forces on the upper proton and compare their magnitudes. Okay. So this is the solution. You have these two protons here. Okay. So you have the r hat, which is the unit vector from one proton to another. Okay. And then the separation distance is r. These two protons are moving opposite to each other, just technically passing through each other. Okay. Remember, class, that these charges, when they are moving, they are producing what? They're producing magnetic fields. Okay. And take note that because of the nature of the charges, if two charges interact, they can do it electrically also. Okay. So therefore, at this separation distance r, these protons that we do have here will experience both magnetic, since they are moving, and then electric forces because of their charges. Okay. Both of them are positively charged, so you expect that both of them will electrically repel each other. But how about the magnetic force? Will they also repel or attract? We will see. Okay. So this is the solution. So for our electric force, we use the Coulomb's law. For the magnetic field, okay, we use this equation. Okay. So Q V I hat cross J hat, okay, over r squared, okay, which is in this form now. Okay. So take note that the V, okay, here is this one. Okay. And then take note that this is moving along the positive x-axis. That's why you have this. So VI hat. Okay. So this proton will produce a magnetic field like this one in this form. Okay. So what would be the force on the upper charge due to the charge below? Okay. So the force on the upper charge, so the force that this proton at the top will experience due to the passing proton would be this. So FB, okay, this is now the magnetic force. We already have the magnitude of the electric field. For the magnetic force, that would be Q times negative V cross P. Okay. Then if you simplify the equation, you have Q squared V squared over R squared, and then negative I cross K will give you positive J hat. That's why you have a positive magnetic force. So somehow it repels also this proton, not only electrically but also magnetically. So the ratio of the force magnitudes is this, okay? FV over FE. By simplifying the equation, it will give us epsilon naught mu naught V squared. Okay. So what does it mean? Okay. What does this equation mean? Okay. Take note that epsilon naught mu naught is equivalent to 1 over c squared, which is the speed of light. Okay. So the speed of light is 1 over square root of mu naught epsilon naught. So here we can see that the relationship would be this. So v squared over c squared. So the ratio of the force magnitude FB and FE would be this, v squared over c squared. So what does it mean? When v is much less than c, okay, I mean the value of your v is much less than c, which is 299,792,458 meters per second. That's the speed of light. Then the magnetic force is much smaller than the electric force. So somehow it gives us an insight that if the particles, if these protons are now moving at the speed of light, okay, just hypothetically, okay, it means that the amount of force electrically is now equal to the amount of force magnetically, because the ratio of v squared over c squared will be equal to 1. But in most cases, these protons, okay, will not move at the speed of light. Much less than, or sometimes maybe 90%, okay, 80% of the speed of light, 75% of the speed of light. You can accelerate them up to 99.99999, okay, percent of the speed of light, but still it's not the speed of light. Okay. Therefore, we can say that the magnetic force, okay, is much smaller than the electric force. It's much less than the effects of the electric force. So if you have this true proton, the significant force of interaction is not magnetic, it's electric. Okay. And especially if these two charges are not moving at all, then there's no magnetic force. But let's say they are moving opposite to each other, okay, the effects of the magnetic force due to one charge is somehow really, really small compared to the effects electrically. So that's it for this problem. A copper wire carries a steady 125 ampere current to an electroplating tank. Okay, as you can see in the figure. Find the magnetic field due to a 1.0 cm segment. So we're just given with a segment of this wire at a point 1.2 meters away from it. If the point is A, point P, okay, I think this is along the y-axis, straight out of the side of the segment. Point P in the xy plane, okay, this one is not in the z axis, it's still in the xy plane, but somehow inclined by 30 degrees, okay, on a line at 30 degrees to the segment, as you can see in this figure. So if you look at the diagram, we should actually conclude that at point 1 and point 2, the magnetic field is into the page. Okay? Take note that if you have a wire, the magnetic field will circle around this wire. Therefore, at the xy plane, okay, the magnetic field direction should be perpendicular to it. Okay? And take note that this cross here, okay, this X symbols here, means that the magnetic field is into the page. So now we use our Biot and Savart law, okay, or Savart law. Okay. So at point 1, we know that the R hat, okay, is along the positive J, okay, which is just up of it, okay, 1.2 meters directly. So if we use our Biot and Savart law, your DL will be that 1 cm segment. Okay, so there is no actual integration that we need to do here unless you want to know the magnetic field for the entire given length of wire. But here we're just given with a segment, so there's no need to integrate. We just need the DL, which is the length of that small segment, and then just operate on the unit vectors. So that's why you have this, okay, mu naught over 4 pi times IDL. So IDL is 1 centimeter negative I cross J hat. That will give you K hat, but in negative because you have negative I hat here. So mu naught over 4 pi, the negative IDL over R squared K hat. You substitute all of the values, okay? So your mu naught over 4 pi would be equal to this. You can use your calculator to verify this. Okay. And then times 125 ampere times 1.0 times 10 raised to negative 2 meters divided by the separation distance from the segment to the point is 1.2 meter, then squared K hat. So you can see that the magnetic force is directed towards the negative Z axis. Okay. The axis which is into the plane. Okay. And with a magnitude of 8.7 times 10 raised to negative 8 Tesla. Okay. So that's for point 1. Okay. You can also check, class, that mu naught over 4 pi is equal to this. You want to check that too. Take note that mu naught has also an equivalent value in Tesla meter over ampere, which is equivalent to 4 pi times 10 raised to negative 7. Okay. Sometimes based on our lecture videos, we are using 1.2566 times 10 raised to negative 6 Henry per meter. Okay. So just be wary of those values. But I think they are both the same. Okay. Still the permeability of free space. Okay. And then for B, okay, at point 2, the unit vector is r hat, okay, which is equivalent to negative cosine 30 degrees I hat plus 30 sine 30 degrees j hat. So you just represent your r hat, okay, in terms of cosines and sines. Remember, your r hat is a unit vector. Okay. So here, since you are inclined by some 30 degrees, you need to get this. And then perform the cross product. So I hat cross negative cosine 30 degrees I hat cross j hat. Take note that I cross I will give you 0, so cancel. You will only have the sine 30, values. Okay, which is negative I hat cross j hat will give you negative, again, negative k hat. So now you have this equation. So mu naught I over 4 pi dl sine 30 degrees over r squared k hat. And then simplifying, substituting all of those given values, and you will have this. Negative 4.3 times 10 raised to negative 8 Tesla, okay, k hat. Okay. So take note, class, that the key concept here is that the magnetic field due to a short current segment of length dl is like that of a moving charged particle. Somehow we can call it as a point current source. Okay, it's just you have the small segment there. So the difference is that the product of the moving charge, particles charge and velocity is replaced by the product of the current and the vector dl in the direction of the current. Okay. So I think this is everything that we need to know about this problem. Okay. A long straight conductor carries a 1 ampere of current. At what distance from the axis of the conductor does the resulting magnetic field have magnitude B equals 0.5 times 10 raised to negative 4 Tesla, about that of the Earth's magnetic field in Pittsburgh? Okay. So this is the solution. Remember that we already solved or derived the equation for the magnetic field, or the expression for the magnetic field due to a long straight current carrying wire, which is equal to B equals mu naught I over 2 pi r. Okay, where your r is the distance between the point of observation to the to the long straight current carrying conductor. Okay, so just extracting R, okay, deriving expression for R would be this. So mu naught I over 2 pi b, and then just substitute all of the values and you will get this. So at 4 millimeters away from that long straight conductor, you will have a magnetic field magnitude of 0.5 times 10 raised to negative 4 Tesla. That's it. That's how easy it is. In the figure is an end-on view of two long straight parallel wires perpendicular to the xy plane, as you can see. Okay. Each carrying a current I but in opposite directions. Letter A, find the magnetic field at points P1, P2, and P3. Okay, and letter B, find an expression for B, magnetic field, or of course we know it as the magnetic flux density, at any point on the x-axis to the right of wire 2. Okay, so let's solve A first. Okay, so remember that these are all vector quantities, so vector addition still works. Okay, so you have 3 points P1, P2, and P3. So we're going to know the sum of the fields at P1, sum of the fields at P2, and sum of the fields at P3. So graphically, you have this one. So you know that B1 and B2 would be somewhat opposite. At P2, they are parallel. And then B1 and B2 at point 3 will be opposite. Okay? Leaving with small values of the fields. Okay? At points 1 and 3, but strong fields at point 2. Okay? So how do make sense it mathematically? So first, we solve for the magnetic field due to the first wire. So B1 is equal to, again, mu naught I over 2 pi times 2D. Why it is 2D? Okay? For B1, this is 1. Okay? Okay? So B1, the magnetic field due to wire 1 is equivalent to 2D because you have D from the center, but this wire is somehow between point 1 and point 2. Therefore, if this is D, and then from the center to P1, that is 3D, that's 3D minus D gives you 2D. That's the distance between wire 1 and point 1. Therefore, this is the magnetic field due to wire 1. The magnetic field magnitude at point 2 would be what? Divided by 4D. Why it is 4D? Okay, this is wire 2. So you have D plus 3D. That's why you will have this magnetic flux density magnitude or magnetic field magnitude, which is mu naught I over 8 pi B. At point 1, okay, we have the magnitudes, but we should know the direction. How do we determine the direction? Right hand rule. So for wire 1, you curl your hand, okay, around the wire, and then the direction of the current would be dictated by the direction of your thumb. If your thumb is out of the page or out of the screen, it means that the field due to wire 1 will wrap, okay, the entire wire 1 in a counterclockwise manner if you are looking directly towards the screen. Okay, but if you are looking at wire 2 now, okay, the thumb will be into the screen, and if you wrap your hand around wire 2, you can see that the magnetic field, okay, is clockwise in direction. Okay, so somehow if you look at point 1, B2 will be upward and B1 will be downward. That's why you have negative J hat here and positive J hat for B2. So the answer, if you add them, that would be negative mu naught I over 8 pi d J hat. Okay? 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 And then at P2, okay, B1 is equal to B2 in terms of magnitude. Why? Because it is symmetric. It is at the middle of wire 1 and wire 2. And take note that since at wire 1, the field is in a counterclockwise direction and wire 2 is in a clockwise direction, it means they will add up. Okay? So at the middle, they have the same magnitude and they will add up due to the direction. what will be the total? That is mu naught I over pi d. And look at that. The magnetic field vector is huge because you add two similar vectors. Okay. How about at P3? So for P3, okay, somehow P3 is closer to wire 2. If you compare that to P1, P1 is a little bit farther than wire 1 compared to P3 with respect to wire 2. Okay? But since similar process will be applied, so you will have the total magnitude, I mean the total magnetic field, which is this negative mu naught I over 3 pi d j hat. Okay? So now we know the sum of the fields at different points, P1, P2, and P3. The question is this: what is the expression for the magnetic field or magnetic flux density at any point on the x-axis? So it means that you are now not limited to just P3. Any points to the right of wire 2. Okay. So now we have this x variable here. Okay. So we don't know at any arbitrary points just to the right of wire 2. Right? We need to know B1 and B2. So of course, for B1, the magnetic field due to wire 1, that would be explained by, okay, so let's say this black line here is the X position. Yeah, it's the X position, this red. Okay, so from the center, from the origin, towards that point, the coordinate is X. If you look at wire 1, that would be X plus D from the coordinate X. For B2, that is X minus D. Then you substitute that to the separation distances, okay, at the denominator, and you will have this expression: mu naught I over 2 pi x plus d j hat minus mu naught I over 2 pi x minus d j hat. How did you get this? Algebra. Okay. So you multiply these two, you cross multiply, okay, and then you simplify the expression. So take note that you have mu naught I times x minus d, okay, at the numerator, minus mu naught I x plus d. So you have plus d minus d, it will be cancelled, okay, because similar opposite sign terms. Then you will only have 2 mu naught I over mu naught I x, right? Okay. And then at the bottom, okay, you will multiply these two terms. Okay, you will have this answer: x squared minus d squared. Oh, I mean the x term will be cancelled. Sorry. So mu naught I x minus d, then minus here. That would be mu naught I x negative x now, because you have this minus negative x minus mu naught I d. Okay. And then you will have this. Okay. So you will be left with mu naught ID, which is negative, over pi quantity x squared minus d squared j hat. So this is the expression for the magnetic field at any points on the x-axis to the right of wire 2. Okay? A coil consisting of 100 circular loops with radius 0.60 meters carries a 5 ampere of current. Letter A. Find the magnetic field at a point along the axis of the coil, 80.80 meters from the center. Letter B. Along the axis, at what distance from the center of the coil is the field magnitude 1/8 as great as it is at the center? So for us to solve this, letter A, we already solved for the magnetic field due to a loop, a circular loop of wire, right? And then you multiply it with n to get the total magnetic field along that axis of the coil. This means, which is equivalent to mu naught n I a squared over 2 times x squared plus a squared raised to 3 halves. Okay? So for us to know letter A, okay, we just need to use this equation and then substitute all of the given values. And then next, we will see that if you substitute all of these values, you will get 1.1 times 10 raised to negative 4 Tesla of magnetic field. And that magnetic field is the magnetic field at point 80, okay, from the center of that solenoid or that coil. Okay. And then for letter B, okay, along the axis, at what distance from the center of the coil is the field magnitude? So you need to compare. Okay. So you're going to equate this, you're going to take this and then substitute the value of 0, which is x, which is at the center, and divide it by 1/8. So that we will know what would be that position. Okay, what would be the distance from the center? And if we calculate this, okay, we will see that the answer will be this, plus or minus square root of 3 over a. You can check it actually. So first is that you square both sides. Okay. So if you square both sides, this would be 64. Then this is times 0 squared plus a squared raised to 3. Okay, and then the same case at this side. And then you will take the cube root of for both sides. Okay? And then you will find that the answer is this. So plus or minus 1.04 meters. Where A, what is your A? That is 0.60, which is the radius of the coil. You can also solve this using our magnetic moment. Okay, this is the alternative solution. Okay, since we know that the magnetic moment will be equivalent to NIA, and then the A is the area of the coil, that's pi A squared. That would lead to this equation, to this value, 5.7 times 10 raised to 2, or 10 squared A dot meter, that square meter. Take note, class, that if we account for mu, which is equal to NIA, and then we replace the NI and A, which is somehow you have pi here, it will become this one. Okay, so this is in our lesson. So using the magnetic moment mu, okay, and then we substitute it here to the equation over 2 pi quantity x squared plus a squared, okay, is raised to 3 halves. The answer will be still the same, 1.1 times 10 raised to negative 4 Tesla. Okay, so still the same. Okay, so this is the first method. This is an alternative solution. Whatever method that will suit you. We derived Ampere's law in our lecture for the magnetic field B, or magnetic flux B, of a long straight current carrying conductor. We're going to reverse this process and we will use the Ampere's law to find the magnetic flux density B for this situation. Okay, so for example, we have this wire. Okay, we know that from this wire that there's a current. We might want to know what would be the magnetic field due to this long current carrying wire. So from the Ampere circuital law, or Ampere circuit law, which is this, okay, we want to extract B. We know that the path that we're going to traverse would be this circle. So the entire path would be from 0 to 2 pi, okay, at a radius r. That's why the circumference of this path, okay, when you take the closed loop integral, will be equal to 2 pi r. Therefore, the magnetic field due to this current carrying wire is equal to mu naught I over 2 pi r. Remember that we solved this, okay, in another using another method. Okay, we use this, I think, using the magnetic flux. Okay, or we uh, yeah, I think the magnetic flux, not the Ampere circuit law. But still, we ended up with the same magnetic field due to a long current carrying wire. I think we also solved this using the complicated integral form. Okay, just imagine your electrostatics problem. Okay, we try to solve the electric field due to a line of charge, to a surface charge, okay, density or volume charge density, and then we do have this overly complicated integral with trig substitution and such. While in Gauss's law, okay, we can simplify the calculation of the problem by enclosing this charge distribution with symmetrical Gaussian surfaces. Okay, so you can enclose it in a sphere or in a pillbox or in a rectangular box or in a cylinder and then solve for the electric field. It's the same case for Ampere's law. We don't need to do this long calculation of integration, trig substitution. We did that for you to appreciate the beauty of Ampere's law. But now that we already have the Ampere's law, so you don't need to go back there and then try to solve it. Okay, tries to solve it using the complicated trigonometric substitution and the integration, unless you wanted to, and then there's a certain geometry for the current distribution that that might require that method. Maybe you can use the Ampere's law for checking and such. Okay, but now we have this magnetic field. Now we do only have the magnitude. How do we determine the direction? Take note, class, that if we do this, okay, if we do this orientation, DL and B are parallel to each other. I mean, the path is parallel to the known direction of the magnetic field using, of course, the right-hand rule. We know that this orientation will tell us that the current is in a positive direction. It will go out. So to follow the right-hand rule, the magnetic field will circle or encircle the current in a counterclockwise manner. Okay, but if DL is but if the D is in opposite direction, it's counterclockwise. Okay, it means that the current is going into the page, not out of the page. Okay, so take note, class, that for us to determine the direction, we know that the current is going out of the page. It is positive. Okay, following the right hand rule, somehow the B appears to be in a counterclockwise. DL should also be in the direction similar to the B, because it would make the entire integral, which is the closed loop line integral of B dot dl, to be positive. If this integral is negative, it must be the current, the direction of the current is negative. Or even the magnetic field is opposite to dl. And if dl is opposite to B, you should think that there's something happening to the current, might be into the page or out of the page. Okay? That's it. Field of a long cylindrical conductor. A cylindrical conductor with radius r carries a current I. The current is uniformly distributed over the cross-sectional area of the conductor. So technically, this is a simplification. If you can remember in our lecture, if the current is in high frequency, okay, the signal is high frequency, it means that the current will just stay on the surface because of the skin depth. In this case, we are just dealing with static conditions or low frequency conditions. That's why the current is uniformly distributed inside the conductor. Find the magnetic field as a function of distance r from the conductor axis for points both the inside of the conductor and outside of the conductor. Actually, we solved it before. Okay, this is just an extension. Remember, you have uh, a, a current carrying wire, a long straight current carrying conductor. Okay, then somehow you can compare it to a long cylindrical conductor because somehow they works the same way. How? So if we look at this, so we were given with a uniformly distributed uh, current density. We know that the current density is I over A, or in a in a complicated or generalized form, which is the surface integral of J dot dA. That's I, right? But for simplification, since this is uniformly distributed, okay, all of the integrals will just be evaluated in a simpler manner. So the integral of dA, that will be just the area of the circle here, the cross sectional. Okay, circle here. That's why it's pi r squared. Okay, if your r is the entire cross section. Okay, the pi r squared means that it's the area of the entire cross section of this long cylindrical conductor. And now we know that if we use these paths, okay, we have two paths here. The first one is that the path has a radius that is less than r, the radius of the long cylindrical conductor, and also another path that is beyond the radius of the wire. So for the first case, r less than capital R, it means that the radius of the closed or the loop or the closed path, okay, the radius of that closed path is less than the radius of the cylindrical conductor. We will see that the enclosed current, okay, by that path is equal to this. Okay, J is equal to pi r squared, which is equal to r squared over r squared. Okay, so it is from this and this one. Okay, so we know that J, the distribution, okay, inside this conductor is uniformly, it is equivalent to I over pi r squared. And now that we have this enclosed current, okay, we know that the area, okay, bounded by this path is equal to pi small r squared. If we substitute this I here to here, you will get I r squared over r squared. Now that we know that we now know the enclosed current, we substitute that enclosed current into our Ampere circuit law, okay, or the Ampere's law. Therefore, it will be equal to mu naught IR squared over R squared. Okay. Take note, class, that the path is very simple. If you integrate that DL, you integrate from 0 to 2 pi, you will get the circumference of this cross-sectional uh, cross-sectional loop. Okay. And that is 2 pi small r. Okay. That's the circumference of this loop. And therefore, we will get, okay, so r squared cancel, and then we have this. So inside the conductor, okay, for any radius less than the radius of the long cylindrical conductor, the magnetic field or magnetic flux density inside will be equal to mu naught I over 2 pi, or small r over capital R squared. So this is the magnetic field inside the conductor. But if it is outside the conductor, you will have this, mu naught I over 2 pi r, because you already enclose the entire cylindrical conductor by that path. Okay. And take note that this is really similar, the same as a long straight current carrying conductor. Technically, there's no difference. Okay. If you have a long cylindrical conductor or a long straight uh, wire, long straight current carrying wire or conductor, the field outside, okay, of those conductors with flowing current would be equal to mu naught I over 2 pi r. It's just the same. So there's no you cannot distinguish it at some point because they're just the same outside. But if you go inside, this is the magnetic field in that conductor. Okay. So this is the distribution. This is the plot of the magnetic field. Okay. So if you're inside the conductor, you can see that the magnetic field is increasing. Okay. Especially you are closing to the radius, okay, the distance r, okay, from the center of the conductor. And then outside r, you will see that the magnitude of the magnetic field produced by this long cylindrical conductor diminishes. Okay. You can also remember from our example in the coaxial cable. Okay, you can see that inside the conductor it is increasing, okay, and then outside it decreases, and then when it reaches the second conductor, it further decreases until at the outer radius of the second conductor, we can see that the magnetic field vanishes because there is no field at all. Okay, if you have this coaxial cable with opposite current directions. Okay. So you can go back to that lecture to refresh your ideas about this one. So this is the simple case because you only have the inner conductor from that coaxial cable. You only have this long cylindrical conductor. Field of a solenoid. We actually solved this one using our arguments of a circular loop. Okay. But now we will try to solve this using the Ampere circuit law. Okay, so you can compare the answer for the field of a solenoid from our previous lesson using that integration using the circular loop, then multiply it by n over L. Okay, which is the turn density. N equal to n, small n equals n, capital N over L, and then we proceeded with the integration, okay, with the trig substitution, then changing the coordinate system from xyz to some theta, okay, and then integrate it for the entire length of the solenoid, and all of those a little bit complicated integration process just to find the field of a solenoid. Okay, we will try to solve this solenoid using the Ampere circuit law, and we expect that it would be simpler. Okay, so a solenoid consists of a helical winding of wire on a cylinder, usually circular in cross section. Find the field at or near the center of a solenoid if it has n turns per unit length, okay, and carries a current I. So this is the solenoid. Somehow here the turns are a little bit wider. I think this is just for the visual, because most solenoid, if you want to design a solenoid with a high strength, okay, that can produce strong magnetic fields, you need these turns, okay, or these coils to be packed together. Okay. So somehow this is the schematic of the solenoid where we will use the Ampere circuit law to do to solve for the magnetic field. Okay. So here you have this integration path. It is just a square, not a complicated shape. Okay. So you have 4 points, A, B, C, and D. And we're going to do an integration path from A to B, B to C, C to D, and D to A back. So this is still a loop. So now we have the Ampere secret law, which is the closed loop line integral of B dot dl. And we will perform 4 integrations because we do have these 4 pieces of path. Okay, from A to B, B to C, C to D, and D to A. Now, you observe the geometry. Remember that you have this solenoid, and inside the solenoid, the magnetic field are almost parallel to each other. Okay? So from point A to point B, there's magnetic field. And the displacement is positive. Along the direction of the magnetic field. It means that the magnetic field is parallel to the direction of the integration, uh, parallel to the path of the integration. Okay, so that dl is parallel to B. So if you have B dot dl, it means that you will have a positive term that you're going to integrate. Okay, and then from B to C, okay, you're going outside. Okay, so the inside of the solenoid to the outside. But if you look at B dot dl, the direction of your dl is now perpendicular to the B. So that's why B dot dl will give you 0, perpendicular, 90 degrees. Okay. Then next is, in a solenoid, we can assume that the field on the sides of the solenoid, you will not have an immediate magnetic field. That's why the magnetic field or magnetic flux density just outside of the solenoid would be equal to 0. So the third integration is 0. And then from D to A, that will just give you 0 because DL and B are perpendicular to each other. So now we're just going to evaluate the line integral of v.dl from A to point B, which in turn is just a simple integration of dl from A to B, which is just the length L. Okay, as you can see, this is just the length L. The next, now that we know that the based on Ampere's circuit law that the line integral of b.dl is just BL, take note this is really simple. Okay, we now know, okay, that b.dl based on Ampere's circuit law is equal to mu naught times the enclosed current. So where's the enclosed current? So look at the loop of coils here. Okay, so somehow this path enclose these lines of currents. Take note, class, that at least for the entire loop of this solenoid, okay, your current this will pass this closed loop many times until the length L. So what would be the total enclosed current? So the total enclosed current would be N times I. Okay? The number of turns, which is capital N, times the current. So how many currents that will pass this integration path? Okay? That would be enclosed by this integration path. That is N. And take note that we do have the N turns per unit length, or the turn density. That is N over L. Therefore, this Ni here can be equal to N times L times I. So this NLI is the totally enclosed totally enclosed current, and then you substitute that in our Ampere circuit law. Now both sides from the left, it is equal to BL, and now it is also equal to mu naught NLI. If you want to solve for the magnetic field, just divide the L from both sides. That will give you mu naught NI, which is the same answer, okay, based on our earlier discussion on the solenoid, which is mu naught capital N over small l times I, which is also equal to mu naught N na small for the turn density times the current. So the Ampere circuit law completely simplified the calculation for us to know the magnetic field of the solenoid. Right? So you might ask when we're going to use the complicated one and the simple one. If the problem exploits symmetry, just like in Gauss's law, that we exploit the symmetry of the sphere, of the cylinder, of the rectangular box or pillbox, okay, we can use that in our own advantage and use the Gauss's law for electricity to solve for the electric field due to that charge density. Same case for the Ampere's law. We can take advantage of using the Ampere's law if we can see that the integration paths are simpler to solve, like a circle or a square or a rectangle and such. But if your device or the geometry of the problem is a little bit complicated, that's the time that you're going to use our complicated integration process. Okay, so I think that's it for the field of a solenoid. Additional to the field of the solenoid, this would be the graph, okay, of the field distribution. So somehow at the center, the magnetic field is mu naught Ni, and somehow at just almost outside the solenoid, okay, you can see that this curve is diminishing. Okay. So at the entire length of the solenoid, the maximum would be at the center, okay, at the origin, and then at the edge of the solenoid, you can see that the magnetic field is now half, until if you go outside of the solenoid, the field goes and goes uh, decreasing. So it decreases as you move further and further away from the solenoid. Okay. The figure on the right, okay, actually the figure below, sorry, shows a donut-shaped toroidal solenoid, okay, tightly wound with N turns of wire carrying a current I. find the magnetic field at all points. Okay. So this is our toroidal solenoid. Okay. So you can have three paths. Okay. Path one, which is inside the donut. Path two is, I think, within the donut. Okay. And then path three to be outside of the donut. We call this shape as toroid. Okay. Somehow this is a cylindrically shaped toroid because there are toroids like the donut itself, it's circular. Okay. Somehow this toroidal solenoid, I think you might have seen this toroidal solenoid in real life. It is usually seen in electronics. Okay, those are the inductors. The inductors, as we discussed in the lesson, inductors are devices that can store and release magnetic energy. Okay. So take note that we're going to take these integration paths for us to know the magnetic field. So this is a solution. So let's take the path number one. For path number one, okay, remember that we need an enclosed current. Without any enclosed current, the magnetic field would be zero. So if you look at path one, there is no enclosed current. Therefore, there is no magnetic field inside. Okay. For path three, which is outside of the toroid, okay, look at the current passing and going out. Okay. So take note, class, that one direction of the current is outside, out to the page, and one direction is into the page. Okay. Imagine that the number of loops, okay, or the number of times those current will pass through the enclosed path, which is path three, would be just the same: out in, and out in. Therefore, all of the fields that would be resulted, okay, due to this opposing current from each side, okay, will just result to zero magnetic field. Okay, so B equals 0 at all points in path 3. So winding passes twice in area enclosed by path 3. So what goes in goes out. Okay, so currents are equal but points opposite to each other. This is the same thing that happens in the coaxial cable with opposite current, if you can remember our lecture. Okay, that's why when you do a closed loop path integral on that device, you will not have any magnetic field. And then for path 2, you can see that the path 2 encloses one side of the inner side of the toroidal solenoid. So it encloses a lot of current. And that would be equal to this. So B dot dl, the closed loop line integral of B dot dl is equal to B times 2 pi r. If you integrate for the entire path, it's 2 pi r. We know that the enclosed current, okay, the total enclosed current would be the current times the number of times it passes that path, or it traverses that path. So how many current lines here? Okay, so let's say it's n. That is mu naught n I. Then equate equate both terms, okay, or equate both expression. They're just the same. So you will have B equals mu naught N, capital N, times current over 2 pi r. So that's the magnetic field due to a toroidal solenoid within the solenoid. That's why, class, okay, to increase, okay, the energy stored in that inductor, okay, or in this toroidal solenoid, sometimes they replace the material, or what they call the core. Okay, they replace the core with a magnetic material. Sometimes you will see some toroidal solenoid that has a magnet inside them. I think even in some motors, okay, they're using magnets within, okay, to increase the magnetic field that you can produce in that solenoid. Okay, the core has an effect. Okay, if you have, let's say, a permanent magnet, and then you get a solenoid, wrap it around that permanent magnet, it will create a much stronger magnetic field due to the combined effect of of the bar magnet or the permanent magnet, which already has its magnetic moments, okay, magnetic dipoles and such, and the electromagnet, okay, that can produce magnetic fields due to the current flow. Okay. So I think this is the end for this problem. Okay, for some summary, okay, so you have these equations and then this geometry, simplified geometries, okay, the ampere circuit law here, the Vio and Sabal law, okay, then the forces between two conductors, you have the magnetic field due to a long current carrying wire, you have the magnetic field due to a current loop, okay, so, and then much complicated problems that we discussed, okay, in our previous lessons. Okay, this is summary. Also, okay, I put a summary of basic current distribution. So you have a long straight conductor, okay, you have a circular loop, long cylindrical conductor, okay, solenoid, toroidal solenoid, you have all of this magnetic field, magnitude, and some, these are the observational point for the magnetic fields. Okay, take note class that we do have the uh, similar forms, not similar forms, but somehow similar list, okay, for electric fields due to charge distribution. You can check the electrostatic sample problems, okay. uh I think it's the note, the PDF, you can check it there, or you can check it in the book. So this is the end of our sample problems in magnetostatics. Thank you.